Not the camera, but yonder camera.
It's very specific.
It is. It is. As opposed to the hither camera. It's completely different.
Hither?
Hither.
Hither
Is
is
that the opposite
here.
of yonder?
Hither is here.
Really?
Yonder is there.
Oh, I've never thought about that before. I didn't know where it
Hither's
was.
here, yonder is
That's
there.
crazy.
What's
Teach
hither?
me more than Mr. Fryer did.
I thought it was.
Y'all
Okay,
tell us your
so
I don't speak.
let me give you some hints on these. First off, Gapshot, make sure all the charges are balanced. Graham, make sure you write out the whole balanced equation.
Wasn't that all there was to
I feel that, yeah, I feel that.
Okay, so to give you some perspective, if you did this right, out of all 10 of them, 2 of them should just involve water.
2 of them.
Okay?
Yeah, the first one.
2 of them, of the 10, should just involve water. Okay?
Actually, not fire, water.
So, let's say, for example, you look at number, I don't know, anybody want one?
Yes.
3?
No, not 3.
No, because this 3 is going to be important in terms of what we're going to do today. So,
We're gonna bolt.
We're gonna melt.
Can you like
here's the first thing that
like
you have
arrange
to
the
have
numbers
right.
the second water one is supposed to be?
What's the formula for aluminum oxide?
Al2Cl3. No, Al2O3.
Yeah. Yeah.
CO2. Where'd you get?
My brain was. I was looking at a different problem. We're good. I got there. Al2O3.
Okay, right? Otherwise known as bauxite. So this is one way that you can get aluminum that you can use to make your cans, and that might needs to get recycled because we only have a certain number of aluminum atoms inside the earth. We can't make more. I'm just saying.
That's so sad.
I'm just telling you, that's the hand that we're dealt. So, this is an ionic compound, right? And you heat it up, it will eventually turn into a liquid. You're gonna melt it. And then you're gonna come in here, and then you're gonna put a cathode, and you're gonna put an anode, okay? When this is existing, and you have to understand this is not existing as a chunk of aluminum and oxygen, okay? These are existing as their cations and anions. So this is existing as Al3 plus, and the oxygen is existing as a free ion as O2 minus. So, it's the same story. What's gonna happen at the cathode? Reduction or oxidation?
Reduction.
Reduction.
Redhead hat.
Oh. The red cat, right? So here's the question. Which one of these is going to get reduced? The aluminum cation or the oxygen? The aluminum, because that's your cation. Ah, that's going to go to the cathode. Shocking as that may be. So your Al, right, is going to do what? Gain 3 electrons and turn into elemental aluminum. So this is one way that you can get elemental aluminum. Now, unfortunately, this is horribly energy intensive because you've got to heat up the aluminum oxide to the point that it turns into basically a liquid. And then, because of the fact that this is a non-spontaneous reaction, then you have to force electricity into the system to make this happen. So this is not a cheap way to make aluminum, because you gotta heat it up, and then, but this is the beauty of recycling aluminum, because you already have it as pure aluminum. You don't have to go through this process of removing the oxygen. So this is why, as you become adults and you go out onto life, if there's one thing you recycle aluminum. Plastic's a bit of a nightmare to recycle because there's so many different kinds. Aluminum cans are just aluminum, okay? Boom, recycle them. We only have a certain number of aluminum atoms that exist on this earth, okay? aluminum is much easier to recycle than plastics are. And plastics you can only recycle a certain number of times. Aluminum atoms, you can recycle them indefinite numbers of times because they're a stable aluminum atom. Okay, so you're gonna make, on the cathode, you would see aluminum begin to form, okay? Now, on your anode, what's gonna happen there? Oxidation, perhaps? I'm just throwing that out as a radical idea. Shocking.
Oxidation of oxygen.
Yes.
What?
So you're gonna get what? O2 and
2 E minus. 4 E minus.
4E minus,
Yeah.
okay? Because then you gotta have 2 of those to balance this out. So what would your N value be? You don't need it, but if you needed it to, what would your N value be? 12. You don't need that. So then you need to balance it, okay? You need to balance it, Sean. So when you balance it, there should be obviously some 4s and 3s in the balanced equation, okay? Because of the fact that you have a least common multiple of 3 and 4. So go with that. When you get to number 7 and you have ammonium chloride, so here's ammonium chloride, NH4Cl, very soluble because all ammoniums are soluble. And I preached this yesterday. In here you have ammonium ions, you have chloride ions, and you have water. Which one is Mother Nature not going to touch?
Ammonium.
Ammonium, way too complicated. Mother Nature goes, you just do you, I don't care, okay? Now, here's the story with chlorine. Chlorine is the one exception to the over-under rule. Nature will actually pick chlorine, even though it's the one up above water, Mother Nature will actually pick chlorine. So on that balanced equation on number 7, you should have chloride ions and water on the reactant side, okay? So one exception to that. On number 9, one of your coefficients should be a 3. So you don't have any coefficients of 3, that's bad. Okay. Anything else? Any other one that you say, I'm a little fuzzy on this one?
Which one's the second water?
Huh?
Which one's the second only water one?
The first one is one of them,
Uh-huh.
Yeah.
and the other one's down a bit.
Anybody
I'll
have
tell you
the other
this,
one?
it's in the lower bottom 5. It's somewhere between 6 and 10.
Okay, so we just did ammonium
So I
chloride. We
think
know it's not molten.
Well, because I think it's the
Because
sulfide.
we don't have.
We don't have sulfide in our.
We don't have sulfur on the charts.
You're right. So what's Mother Nature not
So
gonna
if we don't
touch?
have, okay, so
So it's 6? Yeah.
Yeah, 6 is the other one that just involves water.
I'm so good at
I looked up a number for sulfur.
Yeah, I found
Exactly,
number.
you gotta look it up. How would you Google it?
It's not on the chart.
Real light reading.
It's, yeah. I didn't read, we're supposed to read like 100 pages.
What's the
It's just the same thing as the
Oh.
I see the word
Yeah.
DNA.
But none of it's on the AP exam, so I don't care.
Yeah.
Right. Okay, anything else? Once, twice sold?
Yeah, I didn't read that.
Okay.
Yeah, it's like anything you eat and like physical activity uses yeah, so like
I did.
the potato
I hope you get a good grade. Because I'm just that percent. My rationalization, or my critical thinking skills is off the charts.
Oh, they're more likely to have
Are we doing the last one?
yeah. But Jessica thought that when she turned 32, she started to get Down syndrome.
Me neither.
Yeah, she genuinely said that to the entire class.
Well, Jessica.
Talked about how she was gonna get Down syndrome at the age of 32.
Yeah. You're talking about how if you have a kid over the age of 32, you're more likely to get the Down syndrome. But Jessica took that as you're more likely to develop Down syndrome after the age of 32.
Oh, because
Jessica
it's
doesn't
age.
board.
This is a liquid.
She thought that you're more likely to develop Down syndrome after the age of 50. So she got really scared. I don't know, she got really scared. She's like, wait, am I gonna get Down syndrome? And we're like, no, Lord, that's not how that works.
You're not gonna develop.
Okay.
Okay, Bert, I take it back. We were not sold. We have another question.
What?
We were not, when you said once twice sold, we have another question.
What?
On the molten ones, should the reactants be the compound together
Yes.
since they're not dissolved? Okay.
Yeah. Or you can put a separate, I don't,
It doesn't matter?
Yeah.
Okay. Well, if it doesn't matter to you, it doesn't matter to me.
But if you're gonna write them separately, you have to put the charges on them.
Yeah,
The charges are there.
yeah.
That's-
Yeah, I have the charges, we're good.
Okay, so here's the next big thing. So this, what I'm gonna start with at the beginning should be old hat. You got a strip of zinc in 1 molar solution of zinc ions, you have a strip of copper and a solution of copper. You should, at this point, without hesitation, be able to determine the anode, the cathode. Now, there's your salt bridge. Let's say your salt bridge is made of potassium nitrate. You should be able to tell me which direction that your potassium ions move, which direction your nitrate ions move, okay? Should be able to easily tell me that. You should be able to tell me the calculation value of Enoch. So, go. Where are you gonna start? What are you gonna look for, and what are you gonna look at first? The reduction chart, right? So, figure it out, let me know what you find out. And write the overall reaction. Throw a little shade in there. Throw a little shade in there.
Whoa. I thought this was an art class.
Fancy.
I'm getting them to email my diagrams.
Your shoulders just start to hurt. You're like all of a sudden, ow.
We were so concerned for you.
I mean, you're just saying,
That was some really intense writing.
say, wow. Didn't mean to hurt you by giving you this problem.
I wanted him to give us homework.
Right, really hard.
Workman's comp, I was working the problem.
I'm gonna sue you.
Go ahead.
How long?
I have no doubt.
I'll be your lawyer. I did mock trial for a while.
Okay, so what do you have as the reduction potential of zinc? The straight reduction potential,
Negative 0.76.
negative 0.76 volts. Okay? What about copper?
0.34.
Okay, so right away, which one is going to be more willing to go in the direction of the reduction, in the being reduced? Copper. So, if they both start off at 1 molar, right? So, all that means is that you're under standard conditions. So if that's the case and copper has that higher reduction potential, is the copper going to be my cathode or my anode?
Anode. Whoa, cathode, red cat. Oh my goodness.
So is the copper going to be the cathode or the anode?
Cathode.
That's going to be my copper. My anode is going to be my, okay?
He doesn't have reports.
One G, here we go.
Yes, we're good.
Okay,
I forgot red cat. How dare you?
So-
Terrible mistake.
with the potassium nitrate, which makes up the salt bridge, and I have no idea what happened to my voice today, it's just kind of gone. So, with the potassium nitrate, where are the potassium ions going to go? Are they going to go towards the copper, or are they going to go towards the zinc?
Copper.
Why?
Cations go to the cathode.
Why?
Because you're losing cations.
So what?
Because they're becoming common, because it's equilibrium.
What's the function of the salt bridge?
To make it.
Make it neutral.
Maintain
Neutrality.
neutrality. It's the Switzerland of the story, right? Now, a lot of times, when you see diagrams of salt bridges, it'll be like a glass tube like this, okay? Because that used to be how they would build the salt bridges, because they would physically take a glass tube. It was like the original YouTube, before YouTube became YouTube. And you would fill it up with potassium nitrate, and then you would put copper in the ends of it, and that's how you would build your salt bridge. And then on a small scale, we do the same thing. We just take a strip of like litmus paper, soak it in potassium nitrate, and get the same thing. So if you ever see on the test like this U-shaped thing, that's your salt bridge. Okay, that's how they used to build it, and then said, "Oh, let's just use a strip of copper." Okay. So the cations are go towards the cathode, but understand why. Because at the cathode, which is your copper, what's happening to the concentration of your copper ion? Yeah, so you are decreasing the concentration of your copper ions. So the potassium ions are going, oh, this is bad, okay? We're losing positive charges. So to make up for it, the potassium ions go, we got you, we're going to take your place. Now, over here on the zinc ion side, what's happening to the concentration of your positive charges?
Increase.
Yeah, so you're increasing the concentration of your positive charges. The nitrates go, ooh, we got to balance this out because we don't want to build too much positive charge. So the potassium ions increase, and to balance out the decrease in the positive charges, the anions, the nitrates, balance out the increase of positive charge. So that's why they're going to go in those separate directions. Okay. So what do you have as your E naught value then? 1.10 volts, and your overall reaction is going to be what? Copper 2 plus is going to yield Zn2 plus and elemental copper. Right? Balance, Capshawn? Yes. You were hesitant to answer that question. Okay? Yes, there's nothing to balance. You 2 plus, boom, here we're off to the races. So, in this situation, when you initially set this up, your E naught value is going to be 1.10 volts minus 0.0592 over 2. Now, under standard conditions. What's gonna be the concentration of my zinc ions and my copper ions? 1. They're both gonna be 1. True? So what is my E value gonna be? 1.10. Cool, right? Okay? Because this just becomes the log of 1, which is 0. But over a period of time, and remember, when you do this, and this is handy to keep in mind in terms of what you're actually dividing. I hate this eraser. So what's actually happening is that the zinc ions over the copper ions, or the copper ions over the zinc ions. Zinc over copper. Why? Products over reactants. So this is my zinc ion concentration divided by my copper ion concentration. So here's what I want you to understand, is that as time goes by, what's going to happen to the zinc ions concentration? It's going to go up. So this number is going to get bigger. What's going to happen to my copper ion concentration? It's going to go down. So as a function of time, what's going to happen to the value that you're taking the log of? It's going to get bigger and bigger and bigger, right? So as this number gets bigger and bigger and bigger, will that have any impact on your E naught value? Your E naught value is a set value. That's under standard conditions. It isn't going to change to 1.1. But what's going to happen to your E value?
It's gonna drop,
It's going to drop. Why, Charles?
because the log number will get bigger.
Okay, so you're taking the log of a number bigger and bigger and bigger. Are you going to be taking the log of a number bigger than 1? Yes. So is this in effect going to get subtracted?
Yes.
So as this number, because there's an inverse relationship between Q and E. As Q gets bigger, E gets smaller. Eventually, if you run this long enough, what's going to be your value of E?
0.
Okay? Eventually that's going to reach 0. Okay? Now, when it reaches equilibrium, what do you think, or when you reach that 0, that value is going to be in equilibrium. The whole system is going to be in equilibrium. So instead of Q, once we reach equilibrium, what can we put? K. So E's going to equal 0, right? And I'm just going to put this as a generic E naught, okay? 0.592 over N. And then the log of K. Cool. So what I want to do is that I want to isolate K. Okay? So for all you math nerds out there, this is your moment to shine.
Oh, this is a weird one. Yeah.
How am I going to get K by itself? What's the first thing I need to do?
Add E naught, subtract, or subtract.
How about we subtract E naught?
Well, I like, my brain pulled out the negative and then was adding it over, but that's,
So I get a negative E naught equals negative 0.0592 over N times the log of K. So, Cohen, can we just, since we have two negative signs, we can make everything positive?
yeah.
Cool, right? So then what can I do? So I got E naught times N
Over 0.0592.
divided by 0.0592
So 10 to the whatever that thing is.
equals log of K. Cool.
That's good.
Cool. So then K is going to equal what?
10 to the,
Disgusting.
10 to the grossness.
E naught N divided by 0.0592. True?
Yeah.
Now, let's talk about the ramifications of this. Let's talk about the ramifications. Is N ever gonna be a negative number?
No.
No, it's not. Can E not be a negative number?
Yes.
Absolutely. Can E not be a positive number?
Yeah.
Which one do you want to deal with first, positive or negative? Okay, so let's say E naught is a positive value. What does that mean in terms of spontaneity?
It is.
It is. Spontaneity. Word. It is. Word to the equilibrium. Okay? So, I don't know why that was funny. So that means that this, if it's positive, that means it's spontaneous. Now, let's go back to the math nerds.
Uh-oh.
So, let's go to this one, for example, the one we just did. So we have 10 to the E naught, and E naught was what? 1.10. N was 2, right? And they're divided by 0.0592. So, it's gonna be a pretty big number.
Yes.
So, what do you get?
1.45 times 10 to the 37.
1.45 times 10 to the 37. That's my K value. K, pretty big number at that point?
I'd say so.
Probably.
Now, let's play the what if game. What if E naught had been, I don't know, negative 0.20? Okay, let's just say it's negative 0.20. Okay? Right away, since K is a negative number, what do you know about spontaneity?
No.
It's not.
It's not. It is. It's not. Okay. So now when I do my K calculation, I'm going to have 10 to the negative 0.20. Let's keep N as 2. Divided by 0.0592. Now, before you do any math, is K going to be a number bigger than 1 or less than 1?
Less.
What do you get?
1.75 times 10 to the negative 7.
Now, a whole bunch of things at this point are going to make sense. Look at the ionization of acetic acid, HC2H3O2. Turns into hydronium ions and anions, right? What do you know about, just don't worry about anything else. Is the K value a big number or a small number?
Small.
Oh, it's a small number. Small number. K is a small number. Oh, K is a small number. K is like something times 10 to the negative 6, whatever it is. So, what do you notice about all your Ka values? They're what? Big numbers or small numbers?
Small.
Oh, guess what?
What?
When K is less than 1, K is small. What does that indicate about the spontaneity of the reaction?
It is not.
It isn't. Oh. So, what this is telling you is that if you look at this relationship with this E naught, this is where it all comes together. So if E naught is a negative number, okay, which means the reaction is not,
Spontaneous.
which means your K values are going to be less than,
1.
oh. What do you know about KSP values?
Itty bitty.
Itty bitty.
Really small.
Why?
Cause.
Like
Are they soluble or not soluble?
Not very soluble.
Oh, not so. So if you take magnesium hydroxide, which is very insoluble, and you try and make that ionize, is it going to ionize?
No.
Tiny bit. So is it spontaneous in the forward direction?
No.
No. So the K values are really,
Small.
oh. Now, let's say that you have hydrochloric acid, and that's going to try and ionize. Okay? So let's say you start off with 0.1 molar, 0, 0. So at equilibrium, let's say this is 0.00001, okay? Let's say we get a little bit of molecular form.
Just have to hold on.
So this is gonna be basically 0.1, and that's gonna be 0.1. So when you go to calculate Ka, you got 0.10 squared divided by 0.00001. What do you know about the K value? It's going to be
Hi.
really big, because this is a spontaneous reaction. Now, what if,
Oh no.
You're probably like, here's the pH.
What
calculate
if-
the battery?
E naught equals 0? K would equal 1. So 1 is your break point. Okay? So when you're looking at K values have a break point not of 0, but K values have a break point of 1. So if your K values are really, really big, 10 to the 14th, whatever, what do you know about the reactions? They are going to be spontaneous. This is why you don't have Ka values for strong acids, because it's spontaneous in the forward direction. Now, what about the numbers that are less than 1? Not spontaneous. So give me an examples of 2K values that you've studied that are very small. Ka and KSP. If you really wanted to get fancy, you could throw in KB values. What do you know about all of those values? Really big, really small?
Really small.
Because they're not spontaneous. Big K values are spontaneous. Okay?
I feel like you're about to make us do some really, really bad math.
Oh, Cohen, I would never do anything like that.
Almost had
We
it.
haven't had a long time.
You don't say it out loud.
I'm just saying. Yeah, that's the problem.
That's why we're all
It doesn't
scared right
affect me,
now.
it will only affect him. It will affect you.
Cohen will be doing it at lunch.
No, he won't be. He won't turn it in. He'll get an F for it, because it's the end of the term. He has no more time. Time is running out, Cohen. This is what happens.
I'm already stressed out.
These are the consequences.
You said the word focus.
I don't want to
You
say
did.
that.
Charles really is that parent. You did this to yourself.
He did. I don't.
No, I know that.
I have to say.
I did do stuff at home last night.
How
Okay,
do you feel?
That's how you know it's desperate.
so let's kind of tie this together.
Oh no.
Yay.
So you have molten sodium chloride, right? What do you know about the K value? Big, small? Because you want to try and ionize this stuff, right? If you have molten sodium chloride, the K value is going to be small because molten sodium chloride does not spontaneously change into elemental sodium and chlorine gas, okay? Because that would be bad if it did. Now, you throw in some electricity, your sodium ions are going to turn into
Elemental sodium.
elemental sodium. They're going to grab an electron and turn into sodium. Your Cl minus is going to do what?
Grab 2 electrons. And become
Lose 2
CO2.
electrons and turn into
CO2.
place.
Okay.
We were all like, what?
Okay? So, get me the E naught value for this reaction.
No, it's negative 2.7.
Okay, so what's the sodium E naught value?
Like very, very negative.
Negative what?
Actually, that makes sense. Chlorine does not want to hear it.
And what's the chlorine
Sodium
value?
doesn't want one.
Way up there at the top.
Negative 1.36.
It's really like a fight. It's like,
So, which one's
The case of both.
going to get
Give it.
changed around?
The
the chlorine is 1.36. We
Oh,
already
you already
changed it.
flipped that
We
one?
already flipped
Oh,
it.
okay. So when you add those together, you're gonna get 3, 4.13. So, spontaneous, not spontaneous.
No.
That's what they got.
Like
Definitely
that
not.
thing's gonna do.
I thought it.
At this point, do you have enough information to calculate the K value?
Yeah.
Yeah.
Do you have your not value?
Yeah.
Negative 4.13. What's my N value gonna be? 1 or 2? 2. And divide that by 0.0592. What are you going to get? A really, really big number or a really, really small number?
Really small.
Really, really, really small number. Which means this reaction is going, whoa, this is bad, okay? So, and sometimes you'll get numbers your calculators can't even handle it.
Mine just said 0.
Okay.
Yours just said 0. It's close.
If you get to that situation, just write it as 10 to mathematically whatever you get out of that number. So if you ever get in a situation where your calculator will not give you an answer, just write it as 10 to that power.
That is a lie.
What'd you get?
Negative 139.5.
So it'd be 10 to the negative.
140.
10 to the negative 140?
Yeah.
Yeah.
It's really, 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 really.
That has never happened.
Really small number.
It's not happening.
Okay. Now,
Really regrets everything.
this is where we introduce time.
We introduced.
I'm sorry, what?
Wait,
What?
No!
Stop, go back. Go back to 10 seconds ago when I did not know that existed. Go back.
What, you didn't know that time existed?
You know what I meant.
He just now said 10
Welcome to
seconds ago.
Kitchen.
What?
We discussed time.
Oh, we are so
You're writing so many things that I remember.
What the?
I can't decipher that word count.
What is cool?
Wait a second.
Great to me.
Somebody know,
That's
on your sheet.
Wait, no. This is physics.
That was
Whoa,
funny,
whoa,
guys.
whoa, whoa,
Whoa, whoa,
This
whoa,
is not what.
This
This is chemistry.
Nah,
This is
Bert.
electrical
What are we doing?
engineering.
No.
No, this is
Okay, so
thermodynamics.
right here on this green sheet, you have this handy, it's on your chemistry equation sheet.
E equals M over V.
You have I equals Q over T. You just want me to ignore it and act like it's not there?
That would be amazing. That's what.
Okay, so current is measured in a unit called amps. Okay? So if you've ever seen the breaker box in your house, like most breakers might be rated like at 15 amps. So what that means is the 15 amp breaker can withstand 15 units of coulombs, and that's the unit of charge, okay? So charge is going to be coulombs. And then time is oddly enough going to be in seconds, okay? So if you have a 15 amp breaker, that means that it can handle 15 coulombs of charge per unit of time, okay? If it's a 20 amp breaker, it can handle more. So the bigger the number is, the more time, that more coulombs would pass per unit of time, okay, before it throws. Now, here's how this is going to play out. So if you look at how this is going to play out mathematically, so there's two ways that you can make this door swing. One is you can say, okay, you're in charge of this apparatus, and you want to produce 100 grams of sodium. So you're going to run this thing, and you know that you need to run this long enough so that you end up with 100 grams of sodium. Okay? Cool. And time is going to be your unknown value, right? So here's the story. So you have 100 grams of sodium, right? So right away, what do you think you might want to do with that 100 grams of sodium?
Convert it into moles.
Convert that into moles, right? Molar mass of sodium is
23?
23.0 grams of sodium per 1 mole of sodium. Okay? Now,
Should be like 4.25 or something.
For every 1 mole of sodium that reacts, how many moles of electrons are going to be involved?
11.
1?
11.
Oh, mole of electrons, not number of electrons.
Yes.
Yeah.
Because if you look at the reaction, right, there's a 1-to-1 ratio. Hey.
Not how many has, how many are moving.
Yeah, this is just per mole. So now you've got your electrons.
Don't you move to
Now,
electrons?
Faraday's constant.
if you stop right now, somebody said it, Faraday's constant. What's Faraday's constant?
96,485
96,500
coulombs.
per
It says
Oh, per mole of electrons.
per mole of electrons. Oh.
That's so bad.
it's just stoichiometry.
It is, it's just stoic on steroids. Now, there's one other number that you need,
Angry stoic.
and that's the fact that, let's say that this is a 10 amp current.
Stoichiometry.
So if that's your 10 amp current, what does that mean? That you have 10 coulombs per second. What's this gap, Sean? So I ran out of room. So what can I do with the coulombs per second? So on that last cell out here, I'm going to put, where am I going to put the 10 coulombs, top or bottom?
Bottom.
10 coulombs, and then I'm going to end up with 1 second up there.
Oh, and then 5 seconds.
Oh, and everything cancels out, and I get, dude. So,
How many days is that?
basically, if you want to cancel out the 10, that just becomes 9,000. But what do you get?
I think that took years off my life.
11 and a half hours.
41,956.
41,956 seconds.
Seconds. Actually, it'd be 957 technically.
11.
Okay. So divide that by 3,600,
11.7 hours.
11.7 hours.
Crazy.
That is a long time.
Okay? So you'd have to run that for about 12 hours to get 100 grams. Now, think about this. You go, man, I don't have that much time. What's the only variable you can manipulate?
Amps.
What can you physically manipulate in this experiment?
Mole.
No.
I want less sodium. I'll settle for less. That's why I said high.
I didn't hear you, I'm sorry. Okay?
I heard like 27.
So, if you wanted to do this in less time, would you run more current or less current? Because then in that last cell, you were dividing by a bigger number. But what's your trade-off, though, from an engineering perspective? Well, yeah, guess what? You want to run a 100 amp current, that's going to cost you more, but you're going to be done in less time.
What would a kiloamp look like? Like 1,000 amps. What would that
A lot.
I swear.
I
Yeah.
don't know what you like.
How many
It
amps
was
are
like,
there?
When would I use a kiloamp?
Like if I were to touch something with a kiloamp, what would happen to me?
Oh, there would be no Cohen left.
Where
would be like one and done.
So are we looking?
Yeah,
Are we talking
Because
about-
remember, it isn't the voltage that kills you, it's the amps that kill you.
Oh
The
yeah.
amps?
Yeah,
The voltage does?
Wait, what?
no, amps.
I
That's how
swear.
quickly.
Now, you could also reverse this.
I would've.
All right.
Wait, why do the amps kill you?
Because it's how much
He
current
can't do
is
that.
flowing
This
through
is an
your
operating
body.
Wait, and voltage is not that?
No, voltage is like, voltage is like how high the dam is. Current is the size of the pipe that goes in the water.
Oh, that makes sense.
So here's the analogy, and one chick just asked about this. So, let's say that you have water behind a dam, okay? So that's like your voltage, okay? And then you have two ways that you can get that water out. One, you have a straw,
Yes.
Delicious.
and the other one, you have a big concrete pipe. Do they both have the same voltage? Yes, because they're the same height. But with the bigger concrete pipe, you're going to have more
Amps.
because you're gonna have more water flowing through the pipe. If you want it, it's not a bad book, I've read it. It's a book called There Are No Electrons, okay? No, it's not a bad read. But they explain this in terms of what the guy calls greenies, which are like the electrons that they're designed to move. So, now, you can also change this
Something my
up.
sister would.
You could also take this and go, I could have also said, instead of finding time, I could have said, hey, I'm going to run a 100 amp current for 10 hours. How much mass am I going to produce? So if you're given current and time, you just basically reverse the stoic, okay? All right, we're good? Got it?
I'm actually so good at science. No, I was gonna say I'm gonna be the most steady humanities major you've ever seen.
Oh, isn't it, yes, I'm hyped.
When I be president, I'll be like, I
Now, when you get this, do not flip out. You only have to do the ones that are circled. Okay? Don't look this good. Oh my God, we have to do all of them.
Oh my god, we have to do all of
Only the
them.
ones that are circled.
Oh my god, first
we actually have to do all of
That's
that.
gonna take so long. It's gonna take forever.
We're gonna do all of that? That's so many to do all of that.
That's you and the
I hate women.
This is why.